Hello, my name is Armando Vasquez, and in this video I will present the experimental report on Mariotte's bottle conducted by team number 4. This experiment was carried out as part of the Physical Experimentation and Statistical Thinking course, and in this video I will explain the theoretical background, methodology, results and conclusions of our report. Let's begin with a brief explanation of the experiment and the results obtained, as it is shown in the abstract. This experiment had two objectives: the analysis of the exit velocity of water and the estimation of the gravitational acceleration. Using concepts such as the continuity equation, the Bernoulli equation, and Torricelli's theorem, we measured the exit velocity of water and we compared it to the expected theoretical values that were calculated. The experimental value that we obtained for velocity 2 was 1.1 plus minus 0.2, which was closely enough to the expected theoretical value, which was 1.27 meters per second, showing that it was an insignificant discrepancy between both values. Additionally, we estimated a gravitational acceleration as 8 plus minus 3 meters per squared second, with a percentage uncertainty of 40%. Despite measurement limitations, our results obtained enough precision and fall under the calculated accepted error. For the introduction, let us explore the main topic of this report, which is Mariotte's bottle. The Mariotte's bottle is a system that it is designed to maintain a constant flow rate regardless of the water level that is inside the container, and this property is useful in different fields and applications, such as gravity-fed irrigation systems. For irrigation systems, it is useful since it provides water supply without the need of electrical infrastructure. But in this case, our main goal is to determine the estimate value for gravitational acceleration using some of the parameters that are found in Mariotte's bottle experiment. Let us dive in the theoretical concepts that the experiment relies on. The first one is the continuity equation, and it is considered as equation 1 for our report. This equation ensures mass conservation by relating the cross-section areas of the inlet and the outlet and the fluid velocities in the same points. The second relevant equation is the Bernoulli equation. It describes the conservation of energy in a fluid by a relation of the pressure, the velocity, and the height at two different points. In our report, it is stated as equation number 2. Our last equation is Torricelli's theorem, which will help us determine the theoretical velocity of the exiting fluid, since it involves the height from the exit hole to the atmospheric pressure point that we have inside the bottle. To compare theoretical values with experimental results, we build a Mariotte's bottle using the following components: a 3-liter bottle with a constant transverse section, an atmospheric pressure tube, a drain tube, gum seal, a harvest container, and measuring tape. Some of these components were switched to other elements that were easy to find. For example, the 3-liter bottle was switched for a soda bottle, and in the case of the atmospheric pressure tube and the drain tube, we use straws, and for the gum seal we use Plastiloca. In figure 1, we can see a diagram which is basically a representation of the experiment. In figure 1, we can see a diagram in which our experiment is based. It shows every component and every distance needed for the calculations. It indicates all areas that need to be measured, and it also includes Kuko for reference. The experiment was divided into two parts. First, we measured the exit velocity of the water, and then we estimated the gravitational acceleration. Let us review the first part of the experiment. The figure number 2 shows the experimental model used for taking measurements. And from this model, we took three main measurements. The distance h, from which is taken from the atmospheric pressure tube to the drain tube, the diameter d of the water bottle, and also the diameter of the drain tube. These measurements are seen in table number 1. Now, the process we followed for the experimentation is the following. We measured the height of the level of water inside the bottle from the moment the draining began to the point where the flow stopped completely. And each measurement was taken with 5 seconds of difference. The data collected is shown in table number 2. The initial height of the water is 30 centimeters with a distance of 8.25 centimeters between the drain tube and the atmospheric pressure tube. Now the dotted line represents the height where the level of the water is in the same level as the atmospheric pressure tube. This experiment was repeated 5 times to have a better representation of the behavior of the phenomenon. Now the next step we did was obtaining the value for the cross-section areas needed for the calculations. Using the formula for the area of a circle and obtaining the uncertainty of the measurements taken, our results for the areas with their absolute uncertainties and the percentage uncertainties are shown in table number 3. Using the data obtained in table 2, we use the average of the level of the water from the 5 measurements, and we also obtain the standard deviation error of the mean for every period of time. As a result, we obtain a new data set that it is based in our experimental measurements, and this can be seen in table 4. To visualize better this new dataset, we used Veil software to obtain a graph that would show us the relationship between the average level of water and the time. The graph we obtain is figure 3. This graph can help us understand better how the flow behaves during the experiment. We can see that the first part of the graph shows a linear behavior, and once the level of water is below the atmospheric tube, the flow is no longer constant. Using tools provided by Veus, we created a linear fit for the data. This provided a function of the height with respect to time using linear data. This function can be seen in figure 4, and the y-intercept in this function is the initial value of height, while the slope is the velocity 1, which is 22.0 plus minus 0.2 times 10 at the power of minus 4 meters per second. Using the continuity equation, we can now input the values that we obtained with the respective uncertainties into the equation 15 to obtain our value for velocity 2. And the value we obtain is 1.1 plus minus 0.2 meters per second. Using Torricelli's theorem, the theoretical value for velocity 2 is 1.27 meters per second. Here, figure 5 is basically a diagram that shows the discrepancy between both values that were obtained, the theoretical value and the experimental result. Note here that the accepted value falls into the calculated error margin, which leads us to conclude that there is insignificant discrepancy with respect to our experimental value. Moving to the second part of the experiment, now our new goal is to determine an experimental value for G. To determine a good experimental value, we need more data, and in order to do that, we repeated the previous process for different values for capital H, which, if we remember, is the distance between the atmospheric tube and the drain tube. The initial data was determined for 8.3 centimeters, and our new datasets will contain information for 11 centimeters, 14 centimeters, and 17 centimeters. Or in other words, we will increase the value for H. Here in table 11 we find the results of all the data with the corrected values for height and velocity 1, each for different height. Now, if we wanted to plot these values, we would find that the best approximation for this data would be a quadratic, but in this case what we need is a linear approximation. To fix this, we use the squared value for velocity 1, and what we obtained is now a linear approximation as we see in figure 12. This figure now shows a new function that relates all of our new data through a linear relationship. Using the provided equation 19 to determine the experimental value for G, we use the constant c, which in this case is the slope for the function that we found in the figure before, and we proceed with the calculations for G, including each uncertainty for the values. And we obtain a value of 8 plus minus 3 meters per square second after rounding to one significant figure. Checking figure 13, we notice that the accepted value for gravitational acceleration falls under our uncertainty error. This proves that our experimental value are correct and valid. For the discussion section, we can highlight a few things that we found during the process of experimentation. Taking a closer look at table 11, we found that the larger the value for H was used, we would find a more stable value for velocity 1. This might need further research. It is worth noting since it could be implemented in the future for obtaining more precise data. Now, our gravitational acceleration value contained a relatively large value for the uncertainty, which was about 40%. We could think of several reasons of why we obtained such large uncertainty. Measuring techniques, ideal conditions, or even phenomena that was not considered could affect this value in a way we couldn't notice this time, but that in the future it could affect other kind of measurements. And here we propose several advices to improve our accuracy for these calculations, but at the same time we have to consider that many implications might take calculations to a level where it is more complicated than it is needed, and we might not find what we were looking for. Finally, through this experiment, we validated key principles of fluid dynamics using the Mariotte's bottle. Our results show that it is possible to obtain valid experimental values for the velocities involved in the experiment, and in the same way, we could determine a good experimental value for gravitational acceleration. Although our measurement for G had significant uncertainty, the overall result was consistent with the theoretical expectation. This experiment highlights the importance and the challenges that are found when estimating values, specifically experimental values that are not only found in science fields, but also in engineering and even other fields that we are not aware of. And for now, that's it, and thank you.